Right, dumelang hape bana ba Thabiso. This is where more or less we finished off in part 2. And we see the emergence of the logarithm, which appears as the exponent, all as a result of a multiplication which we discovered from simple arithmetic of addition of the same thing. Now we need to formalize this to be more general. By that I mean we're not attached to a specific number, in this case 3. Right? So to introduce the generality, we are going to consistently replace 3 with a letter. And you'll see in a moment where all this is going. And I will choose, let's choose B. I've got a reason for that. Now you say, okay, what is B? Well, B is any number, right? I will give the formality of B in a moment. It could be 3, as I'm deleting 3 here. Because what we are doing is still outlining the concept that in this case we are adding the same number and we rely on counting. So all those principles, all these principles, Kobala, Dipalo, arithmetic, we're still holding on to them. We're still adding the same thing. Okay? Now from the previous video I made some additions which I will explain in a moment. And the multiplication in this case of the same thing, which is B, we're still adhering to the same principles. The 4 hasn't changed the meaning, that is still an exponent because of the multiplication of the same number. And this, of course, this is still exponential. This is still factorization. You must remember what the objective is. That there are many things that come, that interplay. More concepts are coming in. While we're trying to address the issues of symbols, without which we cannot do anything. It's just like writing the word exponential or BODMAS or logarithm or anything that I've written here. Without the use of the letters, we can't do anything. We have to be able to write. So we need symbols. Right? And the most important thing is that these symbols, like multiplication as operators, they actually come from our natural languages. So the concept of adding the same thing in a short form is a factorized form, which relies on counting. And the multiplication leads us to the exponential, and the logarithmic just appears naturally to us because of counting. Basic principles. Now there's more I want to do about this, but I'm going to need space. So just need a bit of space here. that from this point onwards, while you understand other symbols like implies or equivalence, I can write this factorized form to mean, and I'll write the implies this way, right? Because I don't have space here. To mean 4 multiplied by b. Meaning, from this point, I'm swapping these two around this operator. And the reason why I'm doing that is so that I can introduce you to algebra. Now, what is algebra? Well, algebra comes with axiomatic statements and laws that govern these operators, the addition and the multiplication. And these laws, the law that I've applied here, to say this statement means this statement, this expression, this whole expression can be written this way, where I've swapped for and around the operator multiplied. And that is called the commutative law, as one of those laws. Commutative law. Now, there are other laws which I'm not going to specify. I'll specify them as I go along. But in general, one can look at Zermelo, Frankel, right? Find a good source on Zermelo, Frankel, preferably peer-reviewed, but or from a good source. If Wikipedia gives you this source, as long as it can cite its own sources, that will be acceptable. That will be more reliable. Or Britannica or any other thing. Right. And these are generally called, this is one of what is called axioms of choice. Zermelo-Frankel is one of them. And it will contain these kind of laws. They're more general because they're not only, they also apply to other forms of algebra called vector algebra, so that you get more exposure to mathematical symbolization or notation. Okay, so in general, but here I've applied what is called the commutative law. But I can also go backwards and say, think of this expression as me swapping it around to mean b times 4, and it will land me back here, which means I can write the equivalence, that this expression means this expression, and this expression means expression. Ukulingana, meaning now I can equate the two, that one implies the other, which is also implied, and as a result, they are equal. Now you're beginning to understand the use of the equal sign as a relational symbol, because it falls into these categories. So let me write some of the just a few on the side here. Right. And of course the implies. the equivalence. As relational symbols, so that you continue to remind yourself that there's more, that the equal sign falls into the category of relational symbols. You are relating two things. So, now you ask, what is B? Well, now we can be formal now and specify that B could be an element, and here's a symbol for you. It means element of real numbers, meaning all the numbers that you can think of in the world, including natural numbers. This symbol means natural numbers, which are 1, 2, 3, 4. The first numbers that you get introduced to when they teach you counting from childhood. And I've indicated another symbol here called such that, which is just 2 dots. So I'll explain this in a moment. But now I'm telling you that B is an element, is a number, comes from a set, a universal set called real numbers. Right? And I might like to specify restrictions. And most commonly, the restriction I'm going to specify would apply to this statement when I've reached the exponential form. And you'll see in a moment. But for now, let me relax on. But if I wanted to, I can exclude 0. This means all the numbers except 0. Right? And I can specify more than one of them and say 0, 1, or, 2, meaning I'm excluding these numbers for what B is. So B is anything, any number, except 1, 0, 1, or 2. So this is more notation. Now, it will feature in, especially when we look at, and we'll understand why we have to have a restriction. Now, we have chosen mathematically any number that we can add to itself or we can multiply by itself. But now we need one more thing that should give us control on how many times do we want to add the B and how many times do we want to multiply the B. We don't have that yet. So it's going to come in red. Right? And you should guess by now that, no, in terms of the multiply, right? Because this statement, this expression means because of 4, the multiplier 4, we will add B to itself 4 times. 1, 2, 3, 4. Now I want to be variable now. I want to have control to say I want to add it 1,000 times. And tomorrow I want to choose another thing for the same B. So how do I represent it in mathematics? Well, we bring another symbol, another alphabet. Another alphabet. Now I want to write it in red because it's going to play a major role. And literally we call it X. especially for high school and, up to high school. Now I want to be able to do the same thing here and say X. But now this statement is invalid because I can't do it 4 times because I don't know what X is. X is just a symbol. You are the one who's supposed to choose it now and say it's 4. The same thing here. You are the one who's supposed to choose it. You must come up with a number called X. You choose a number. And you can also say X is an element of the real.